Okay, to practice more orbital diagrams and electron configurations, and also to introduce some very important ideas related to ions, which we're familiar with, which we've seen at multiple times throughout the semester. What we're going to focus in on at the beginning of this video is the electron configuration or orbital diagrams of ions. We know that these guys are related. If we know one, we know the other. But like I said, we're just going to get some more practice here, and we're also going to look at ions, okay? The electrons still fit in the slot, so really nothing changes. What we just have to remember is what it means to be a cation or anion. We have to remember that there's an electron sort of count change. The total electrons has been affected by, all right, the presence of this charge, essentially, okay? So let's look, and just for the heck of it, let's do an orbital diagram for Mg+, okay? Now, Mg+ has how many total electrons? Mg by itself, when it's neutral, has 12, right? So Mg plus has 11 total electrons, right? That's the same total electrons as Na that's neutral, if you look at a periodic table, right? When things have the same number of electrons, we say that they're isoelectronic. So Mg plus is isoelectronic with Na. Now, why is that important? Because the electrons are going to fit in a slot. So if you can write Na, it is the same as Mg plus, right? The orbital diagram, the electron configuration, all of that. Because they're all isoelectronic, if you can write, all right, Na's orbital diagram, which you definitely can do, is the same as Mg plus, okay? So if we look at this now, where do we start? As always, we start with the 1s, which has an m sub L of 0. There would be 2 electrons there. Following along the periodic table, we then go to 2s, because we go down to a new period. The second period has 6 slots. 1, 2, 3, 4, 5, 6 for your 2p electrons, right? And then if we look at our electron count now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need one more electron because Mg is missing an electron if it's Mg plus. And so we go down to the new period. Whenever we go down to a new period and we're on the left-hand side of the periodic table, we're filling S's. So this will be a 3s, right? And there's 1 electron there, okay? So let's look at selenium minus, and let's do an electron configuration just to practice, okay? So selenium minus has 35 total electrons. So selenium minus is isoelectronic with Br. So just to reinforce the point I was making earlier, all right, the electrons fit in the slots. If I can write an atom that has 36 electrons, every atom that has 36 electrons has the same electron configuration. So if you can write Br and its electron configuration, and I'm sure you can, then you can do it for selenium minus. So selenium minus, right, has 35 electrons. The first 2 go into the 1s, then we go into the 2s, then we go into the 2p, right? And there's 6 electrons, so you see how these guys relate to each other, right? Now selenium has a lot more electrons than Mg+, right? Especially selenium minus, right, which has an extra electron, all right? So now we go into the 3s. Look at the periodic table. The next one that we start to fill is the 3p, because we go across, right, the period. And remember that the 3 P's are filled, and then we go to the 4 S's. Now we're in the transition metal block. Remember that we filled D's in the transition metal block, but the D's lag one behind. So even though we're in the 4th period, we start to fill the 3 D's. There would be 10 of those, okay? And then there's 1, 2, 3, 4 electrons to get to selenium, but we need an extra one because of this minus sign. So it would be 4p5, right? 4p5, okay? So hopefully you can see now, all right? Just with ions, it's the same sort of process. You have your total electrons, they're fitting in the slots. So if you have a positive charge, you take away electrons, right? Because they're missing electrons. And if you have a negative charge, there's extra electrons there. So you put more on, but they go into the same slots, all right? Just real quick, if I was gonna just modify this slightly, if we were gonna look at using a noble gas shortcut, and sometimes the problems will ask you to do that, right? Mg plus looks like a neon core. So I would put that in square brackets and then a 3s1, right? Selenium minus looks like a argon core, right? And then you get into filling the fourth period information, which is 4s2, and then the 3ds and the 4ps, okay? So that should help review, and it's another example related to the last video, electron configurations of ions, right? The last part of this video, what we're going to talk about are other bits of information we can get from the periodic table, right? And we're going to focus in on 3 different ones this semester because of the time constraints that we have. And so the other thing that we can do when we look at a periodic table is we can see what are known as periodic trends. Right, periodic trends. And these are physical properties of atoms that are related to their placement on the periodic table. Right? And the first one we're going to talk about is effective nuclear charge. So what does it mean to have an effective nuclear charge, right? Well, we know that nuclear charge is Z, right? And we went over that earlier in the semester. So this is our whole number, right? For an atom on the periodic table, it's Z. It's the number of protons. What effective means, right, and what effective refers to is, right, what the outer electrons feel. And the outer electrons feel a charge that's less than Z. They feel an effective charge. They don't feel Z. They feel a charge that's less than Z, right? Well, how do they feel a charge that's less than Z, right? Electrons of lower N shield the outer electrons. Right? Electrons of lower N shield the outer electrons. Essentially, they're in the way. So even though, all right, the number of protons tells you the total positive charge of a nucleus, right? When there's negative charge in the way, the outer electrons don't see that full charge. Those outer electrons see something that's less than that full charge, okay? So I'm going to draw a picture that sort of shows that situation, right? We label Z effective ZEFF, and we remind ourselves that it's less than the full charge, right? And only outer electrons, right, are going to be affected by the Z effective idea. Only outer electrons sort of are experiencing this Z effective that's less than Z. So the easiest thing to do is to look at something like lithium, right? So if I look at lithium in the periodic table and I think about its nucleus, all right, lithium has 3 total protons because its Z is 3, and so it has a positive 3 charge. Lithium has 3 electrons. If we look at lithium in its orbital diagram, right, lithium has 1s, 1, 2, and then 2s, 1. So what ends up happening is, right, we can picture where these electrons live. Now we know, excuse me, we know that s orbitals, okay, they have an m sub l equal to 0, which means that they show up as a set of 1, okay, and they look like spheres. So these 2 electrons, these 1s electrons, they live in a sphere, all right, around this nucleus. Right? They live in a sphere around this nucleus. So there's the area they live. And I'm going to put E minuses inside here. Well, let me use a different color maybe. I'm going to put E minuses inside here. So you can see where these 2 1s electrons live. Now, the 2s electrons, they are at a higher energy. Okay? And we know that because they have a higher N. Now, what does a higher energy mean for things that are charged? Remember, low energy, right, is when negatives and positives are really close to each other. A positive object and a negative object, they attract. They want to be stuck together. So the closer, the better. So the 2s looks like a sphere, but it looks like a bigger sphere. And in fact, the 2s electrons, right, live in this region, okay? They live in this spherical region because it is an S, but they live further away because they have a higher N. So here I'll draw the 2s electron in black, right? So there's the 2s electron, so it lives in that space, right? So now let's think about what these electrons see in terms of charge. This electron here looks to the nucleus. Oh, it sees a full +3. There's nothing in the way, okay? Same thing for this electron, right? It looks at the nucleus and it sees a full +3. All right, no issues there. What about this outer electron? This outer electron starts to look towards that +3. And remember, if it could feel that full +3, it would feel that full Z of charge, because Z for lithium is 3. But what's in the way? All right, these electrons. So it doesn't just see positive when it looks in here. What does it find before it gets to positive? It sees some negative. So I'm just going to kind of draw this as a squiggle, right? Because it's not feeling the full +3, all right? These inner electrons have screened this outer electron, and we call that screening shielding. They're shielding this outer electron from the full +3 charge, okay? So this is effectively Z effective. This is an idea that we just described in words, right? Does this thing see, right, a full +3? No. It feels something that's going to be less than +3 because there are minuses in the way, right? So this happens as you go across a period. And whenever we learn a periodic trend, right, this is what we do. We learn what happens across a period and what goes down a column. So if you think about going to beryllium then, what changes with beryllium? Well, there's still these 2 electrons that are going to be inside here that are going to screen the full +4, right? And so on and so forth, right? So what we do is we develop this trend that says, okay, well, as you go left to right on a periodic table, all right, you're shielding with the same electrons. Like if you go across that second period, right, there are 2 1s electrons that shield everything, right? Now the charge of the nucleus is increasing, but the shielding stays the same, right? So as you go left to right, Z goes up and shielding stays the same. Think about going to beryllium, then to boron, the carbon, and drawing that picture that I drew. And even though the p orbitals would be up and down, there's still those 2 1s electrons that are in the way. You have the same shielding but increase of Z. So left to right across the periodic table, Z effective goes up. You're adding protons to the nucleus with the same shielding, so effective nuclear charge is going to go up. Even though it's smaller than Z, if I do throw more Z in there, all right, Z effective is going to go up. Now, top to bottom, what happens when we go down? We go to a new period, all right? So even though, all right, our Z goes up. Think about going from lithium to sodium. So Z went way up, all right? It went from a 3 to 11, right? But here's the thing. Shielding also went up. Because for lithium, there would be 2 electrons shielding the outer electron. But for sodium, there would be 10 electrons shielding the outer electron. It wouldn't just be the 1s electron shielding the sodium electron. It would be the 1s, the 2s, and the 2p electrons that shield the outer electron. And shielding has a much more dramatic effect on things than Z. So shielding goes way up. So even though Z goes up, shielding goes up, and this matters more. And so as you go top to bottom, Z effective goes way down. Okay? So what the outer electron feels is more pull as you go left to right. And what the outer electron feels is less pull as you go top to bottom, all right, down a column on the periodic table. And this actually helps us explain the other two trends that we're going to discuss, all right? And so the next trend that we're going to discuss is atomic radius, which is another way to say atomic size, right? And you can see on slide 14 of our slideshow, our chapter 6, chapter 7 slideshow, right? You'll see information related to atomic radius, but it's just a periodic trend that depends on Z effective, all right? A higher Z effective means a smaller radius. Now, why is that? It's all about that outer electron, right? Literally what you think of is a nucleus here, right? And there's a bunch of inner electrons. But this outer electron, the one that's affected by Z effective, right? It determines a certain radius, okay? So it determines like the overall size of the atom, right? So if this guy is held with a strong Z, what's it gonna do? It's gonna come in and you'll have a smaller atom. And if this guy is held with a weak Z, it's not held as much. And then what are you gonna have? You're gonna have a bigger atom. So atomic size, which is based off the radius to the last electron or to the outer electrons, right, is affected by Z effective because it's how much pull, right? It's affected by Z effective because how much pull there is determines, right, how close this electron is to the nucleus. More pull, it's closer. Less pull is further away. So if I know the Z effective trend, then I know the atomic radius trend, and you can kind of see this on slide 14. Now, there are some exceptions, but we're not going to focus in on those exceptions. We just want to see the general trend. What happens left to right on the periodic table? Well, left to right on the periodic table, what's happening in Z effective? Z effective is going up. So as you go left to right on the periodic table, your atomic size or your atomic radius, it goes down. So if you look at lithium to beryllium, beryllium is actually smaller. Beryllium has a +4 in the middle, right? And the same shielding as lithium. So beryllium is held tighter. Boron's even smaller, carbon's even smaller, nitrogen's even smaller. Across the periodic table, atomic radius goes down. Well, then what about top to bottom? What if I compare lithium to sodium to potassium? What if I go down a column? Well, what happens as you go down? Z effective goes way down. Now look at this. This is an inverse relationship. So Z effective is going down. So what happens to the radius? The radius gets bigger. If Z effective is going down, the outer electrons are not held as tightly. So as you go top to bottom, atomic radius goes way up. Right, goes way up. So the types of problems you'll see will have you just kind of use this trend, maybe compare a couple atoms. Let's just do an example. Let's rank fluorine, chlorine, and oxygen in terms of size, right? And I want to do this in terms of increasing size. Sometimes you're asked for decreasing size. Just make sure you pay attention to the wording of the problem. But increasing size, so I want the biggest atom here, the middle atom here, and then the smallest atom here, okay? So fluorine, chlorine, and oxygen. Well, let's look at F and O, and let's order them first, because they're in the same row. So these are actually left and right of each other, okay? So F has a higher Z effective. F is further to the right on the periodic table. So F is definitely smaller than O, okay? So, how does Cl relate to F and O? Well, it's actually down, right, a column, okay? You have to go down to the next period. Oh, well, if I go down, what happens? Things get bigger. Okay, so then this sets my trend. F would have the highest Z effective, so it would have the smallest size. O Z effective would be in the middle, so its size would be next. And CL has the biggest Z effective. Sorry, CL has the lowest Z effective. CL has a ton of shielding. CL has the lowest Z effective, so it has a bigger size. It's down on the periodic table, right? So in terms of increasing size, right, CL would be the biggest and F would be the smallest, right? And sometimes problems will show you like these greater than signs, and the way that you read this is, okay, F is less than 0 is less than CL, or you can think about it as CL is greater than O, which is greater than F in terms of size. Now, if you're doing decreasing size, just remember to flip everything, but I just wanted to show you one example related to, how you'll see problems on Chem 101 and in your book, okay? The final trend we're going to worry about is electronegativity. And we will need this in the next section. Electronegativity. All right. We're going to need this in the next section because it depends on, what it matters is, in terms of electronegativity's effect in the real world, is how things that are bonded feel each other. Okay? Electronegativity, right, is an atom's ability to pull electrons close to it if in a bond. So the reason this is going to be more relevant in the next section is we're going to talk about bonding, and we're going to draw pictures of bonding. And what we're going to need to realize is that when we draw shared electrons, right, electrons in bonds aren't shared equally. Now, what happens is this idea of electronegativity tells us how that unequal sharing manifests, right? And if you have a higher electronegativity, and I'm going to use En, right, to abbreviate electronegativity. If you have a higher electronegativity, then the electrons in a bond, right, spend more time near that atom. Now so we're going to learn the trend, and then I'll show you an example, and I'm going to draw a picture of what we mean about unequal sharing, okay? So the trend is all about F, okay? So if you look at slide 27, the way I like to remember the trend is it's not like top to bottom, left to right. It's all based off F, and F is the most electronegative atom. Right? It has the most electronegative. It has the most electronegativity. It's the top of the hill, right? And then from F, right, as you go this way, electronegativity decreases. And you'll see this on the slide. As you go this way, right, electronegativity also decreases, but there's a big dip going from F to Cl. So we just kind of remember that F's the top of the mountain. You go down as you go this way, you go down as you go this way, okay? But the first step down this way is pretty dramatic. The only other thing we have to remember with electronegativity is where H sits, okay? Now, if you go down this way, eventually you'll see C and you'll see B. So C, right, is more electronegative than B because it's closer to F. But H actually fits in between C and B. So H is, all right, less electronegative than C, but it's more electronegative than B. And like I said, this will matter when we start looking at molecules and shared electrons in molecules and what structures we see. Because unequal sharing means that these little things we call partial charges show up, right? So F is more electronegative than O, N, or C, and it goes down in that direction. F is more electronegative than Cl, Br, I, okay? Just remember, F is the top of the mountain. Let's see what we mean with an example. So let's look at a simple example like HF. Now HF in the gas phase is not an acid. It's a covalent compound, right? And we're eventually going to see that we can draw a bond between H and F, right? Next sort of video, we'll go over how, there's also electrons on F that we represent as dots. And then these dots are not involved in the bond, but this line represents shared electrons. So we'll go over how we get that picture in a bit. But essentially, in the next video, we see shared electrons there, right? So there's 2 electrons involved in an HF bond. So here's my H and here's my F. So let's kind of draw what the orbitals look like, okay? Now this is actually a really complicated process. So we're going to draw these bubbles just based off electronegativity. There's all this math stuff that happens in the background, okay? So what I'm going to show you is a bubble that represents, all right, if the electrons were shared equally. So if the electrons are shared equally, we have these 2 electrons, then they're going to spend, okay, equal amount of time near the H and the F. So this bubble represents the space that they live and how much they like to be in a given space. But now that we've learned about electronegativity, do H and F have the same electronegativity? No. F is way more electronegative. So these electrons that live in this space, they actually want to spend more time near F. So this is not the mental picture we have for how the electrons live and where they live. They spend way more time near F because F has more electronegativity. So in terms of where you'll find an electron, what this bigger bubble represents, and the red bubble is the actual bubble that you would see for HF, because we're saying that they have a difference in electronegativity, okay? What this tells you is that the electrons spend way more time near F, right? There's more electron density there. You'll find them living near F more than H. Well, then if you look at this side is less negative than this side. This side of the molecule where the H is, right, it has less electrons in general. A little bit of the electrons want to live there, right? You'll find the electrons there a smaller amount of time relative to them with finding them near F, okay? F pulls the shared electrons more than H, right? So what we say on this side is that it has a partial positive charge, right? It's not fully positive because there's still some electrons there, but it has a partial positive charge, and this is the Greek symbol delta. It's a small delta, not the capital delta we were using in the thermodynamics chapter. Now, if the electrons are here more, then they have a partial negative charge. Because it's not like a full negative. It's not like both electrons are over there and it's actually picked up an electron, all right? But it's partially negative because you see the electrons on that side more. So electronegativity is a trend that's all about F. And you can see from this picture, the more electronegative, it's not like an equal sharing of electrons. The more electronegative, the more the electrons spend near that atom. And if they spend time near that atom, you pick up a partial charge, right? And if you're picking up a partial negative over here, that means on the opposite side, you would have a partial positive charge, okay? So hopefully you find this video useful. The beginning part was a review of last video and then also representing ions in terms of their electronegativity, in terms of their electron configuration and orbital diagram. And then we finished up with periodic trends, okay? So our last sections that we deal with are now coming up with ways to represent, all right, shared electrons in atoms, and then being able to relate that to physical properties like where partial charges might be through an analysis of electronegativity. So now we kind of say, okay, we get a better idea of how electrons behave. They're strange, they're quantum mechanical. How do we use that knowledge to come up with simple models that let us represent bonds, all right? And that'll be what we do next time.